The purpose of this video is to explore two linked concepts. The first one is pooling. The second is shrinkage. These are associated with hierarchical models, and they're going to occur irrespective of whether the mode of analysis is Frequentist or Bayesian. To explore these ideas, I'm going to take an example from Kruschke, pages 240 to 245 with a few modifications. And the whole idea is that we've got 28 students. We're interested in their academic ability. And so we give them a test with 10 questions and get the number of correct answers, which we will refer to as score. So here's a histogram of the data. There's score. There's the count of students. So you can see that there's one student who got 8 out of 10. There were 8 students that got 3 out of 10. And so we're going to now analyze those data using runjags. So here's our directed acyclic graph. And we'll start at the bottom, as usual, with the likelihood function. And the two notions of the likelihood function is that first reflects the process that gave rise to the data. So we're going to assume that these 28 values of score I, each one of those arose as a random draw from a binomial distribution with n is equal to 10 questions, n is equal to 10 trials, and this value theta I, which is the probability of success, the probability of getting a correct answer. And we're going to use theta I for each student as a measure of academic ability. Second feature of likelihood, of course, is that the data are constant, and theta is going to vary. So in this particular case, we've got a binomial distribution. N is going to be equal to 10. Y is going to be the value of score. And runjags is going to go on its random walk. And we're going to get the posterior distribution of 28 values of theta, which is going to be our index of academic ability. So that's our likelihood. Then we've got our prior. And our prior is going to be parameterized with omega and kappa parameters instead of A and B parameters, something that was described in the first video, but I'll go over again. So in that first video, we said that typically we parameterize our beta distribution with A and B parameters. And when we did the handedness study, we had a beta for 2 because we knew of 4 successes, 4 right-handed people, and 2 failures, 2 left-handed people. And the alternative parameterization is going to have omega, which is the mode of the beta distribution, and that's going to be calculated by the formula shown here. If we substitute 4 and 2 for A and B, then this thing turns out to be 0.75. In the case of kappa, that can be referred to as concentration. It's just the sum of A and B. So in this instance, using these values, we would get 6. So the configuration of the beta distribution with this alternative parameterization is shown here. So it's a beta. And so A would be this thing, B would be this thing. And in fact, we can see that, or you can calculate that if you were to substitute 0.75 for omega, and if you were to substitute 6 for kappa, this thing would once again return to being a beta 4-2 distribution. So now let's think about this concept of pooling and shrinkage. And it's really not that all complicated. So here we have a hierarchical model. And one of the things that makes it a hierarchical model is that we're not specifying the values of these parameters. We're just indicating them as symbols, omega and kappa. And the posterior values of omega and kappa are going to be determined by runjags as it goes on its random walk. And those values are going to be a balance between their hyperpriors. And their hyperpriors are going to be, as shown here, a gamma distribution for kappa, a beta distribution for omega. the posterior values of omega kappa are going to be a balance between the hyperpriors and the data. So that's why we have this concept of pooling, because the raw scores of each individual student are going to determine the posterior values of omega and kappa. All the data from all the students are going to determine the prior. So that's where the pooling comes in. In terms of the shrinkage, if we think about our object of interest, which is these values of theta, they're going to be a balance between the data and the prior being determined by all the individual students. So if we put some more flesh on that, if we consider the outcome of runjags random walk, we would have it turned out that the posterior mean, and this is all available in code on eClass, the posterior mean of omega was 0.44, and the posterior mean of kappa was equal to 54.3. So here is the prior. So there's the prior there, based on omega being equal to 0.44 and kappa being equal to 54.3. This is the raw score of student number 28 with score proportion of correct answers of 0.8. So there's 0.8 right there, and there's our prior. There's our prior with its mode at 0.44. So if we think about the posterior, it's going to be a blend of this, and it turns out to be 0.53. So we can see that what's happening is there's shrinkage. There's shrinkage of the raw score here towards the mode of the prior, towards the mode of the prior, which is determined by all the data. So that's why we have these link phenomena of pooling and shrinkage, and we can see that here for all of the students. So with the triangles, they represent the proportion correct. So these are the raw scores shown here. And theta, those are the values of academic ability, the posterior values of theta I generated by runjags. And you can see here that in every instance, those values are shrunken towards the mean. So again, the example that we just went over was for student number 28, the raw score was 0.80, but the posterior mean for theta, academic ability, was only 0.53. So now there's some additional considerations. The first of these additional considerations is the effect of the amount of data on the posterior distribution of theta in the experiment involving students and their scores. So here's our DAG, and what I'm going to do, I'm going to redo the analysis, and for each one of the students, I'm going to keep the proportion of correct answers the same as done previously, but now I'm going to change n is equal to 10 to n is equal to 100 and see what effect that has on the results. So what's going to happen is pooling and shrinking. Why? Well, if we think about the prior is going to be a balance of the data for all of the students and the hyperprior. And so because the data for all the students goes into the prior, that's why we have pooling. In terms of shrinkage, when we have the estimate of theta for any one student, that's going to be a balance between the prior, it's determined by the data for all the students, and the raw data for student number I. So you can see that here, the effect of changing n is equal to 10 to n is equal to 100 questions is that previously this student 28 went from a raw score of 0.80 to 0.53. Now that we've got more data for that student, the balance is going to swing towards the data for that student. There's going to be less shrinkage, and it's going to go from 0.80 to 0.77 for our estimate of theta. And then the second consideration is, well, shrinkage is going to occur. Do we want it? Well, if we're dealing with students, we're probably not going to take this student that scored 80% and tell them that their final grade is going to be 53% based on the performance of their peers. On the other hand, if we're dealing with drugs, let's say we're doing a screening study for drugs, and based on performance, we select this one. We might naively expect that its performance is going to be 0.80. But one of the reasons that this particular drug performed so well was just by chance. And as a consequence, this shrunken estimate might actually provide a much better estimate of the true efficacy of that drug. So, those are a couple of extra considerations. I just want to summarize now. The basic idea of pooling and shrinkage is that the prior is determined as a balance of the hyperprior and the data for all of the students, and that's why we get pooling. And the posterior of any one student is determined by a balance of the prior of all the students and the raw data for any particular student, and thus for any one particular student, the value of theta is going to be drawn from their raw score towards the mode of the prior distribution.